Welcome. Today, we're going to solve an interesting problem. It's often presented as a Harvard University entrance exam question, but the truth is, it's a great example of how to combine algebra and logical reasoning to find a solution. The problem asks us to find the value of a in the equation, a to the fourth power minus 16, all divided by a minus 2, equals a to the third power. It looks challenging, but by the end of this video, you will be able to solve this problem by applying a few key algebraic techniques. Our learning objectives are, first, to recognize and use the difference of squares formula, and second, to solve the resulting polynomial equation. Let's start by analyzing the equation. The first thing we notice is the denominator, a minus 2. Anytime a variable appears in the denominator, we need to be very careful. A fundamental rule of algebra is that you can never divide by 0. This means the denominator, a minus 2, cannot be equal to 0. If it were, the equation would be undefined and meaningless. So we must add this crucial condition right from the start. This condition simplifies to a must not be equal to 2. This is an extremely important piece of information that will come back to help us at the very end. Now, let's focus on simplifying the left side of the equation. We have a to the fourth power minus 16, divided by a minus 2. The key to simplifying this is to factor the numerator, a to the fourth power minus 16. We can see that this is in the form of a difference of squares. Remember the difference of squares formula? It states that a squared minus b squared equals a minus b times a plus b. In our numerator, a to the fourth power is the square of a squared, and 16 is the square of 4. So we can write it as a squared squared minus 4 squared. Applying the formula, this factors into a squared minus 4 times a squared plus 4. But wait, we're not done. Look at the first factor, a squared minus 4. This is another difference of squares. It can be factored again into a minus 2 times a plus 2. This is the crucial step. So, our original numerator, a to the fourth minus 16, fully factors into a minus 2 times a plus 2 times a squared plus 4. We have factored our expression by applying the difference of squares formula twice. Now let's substitute this factored numerator back into our original equation. Our equation becomes a minus 2 times a plus 2 times a squared plus 4, all divided by a minus 2, equals a cubed. Here's where that condition a is not equal to 2 becomes important. Since we know a minus 2 is not 0, we can safely divide both the numerator and the denominator by it, without changing the equation. The a minus 2 terms cancel each other out, simplifying the left side significantly. This leaves us with a much simpler equation. A plus 2 times a squared plus 4 equals a cubed. Notice how our condition, a is not equal to 2, was essential for this cancellation. We've now simplified the equation down to this. Our next step is to expand the left side using the distributive property, or FOIL. We multiply a by a squared, then a by 4. Then we multiply 2 by a squared and 2 by 4. This gives us a cubed plus 4a plus 2a squared plus 8. The equation is now a cubed plus 2a squared plus 4a plus 8 equals a cubed. This looks promising. Notice that we have an a cubed term on both sides of the equation. If we subtract a cubed from both sides, these terms cancel out, simplifying our equation even further. This is a common and satisfying moment in algebra. We are left with a quadratic equation, 2a squared plus 4a plus 8 equals 0. We have successfully reduced the problem to a standard quadratic form. We've reached our final form of the equation. Let's solve this quadratic. 2a squared plus 4a plus 8 equals 0. First, we can simplify this equation by dividing all terms by the common factor of 2. Dividing by 2 gives us a squared plus 2a plus 4 equals 0. This makes the next step of solving easier. Let's use the quadratic formula to find the values of a. Remember, the quadratic formula solves for the roots of any equation in the form of ax squared plus bx plus c equals 0. The formula is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our simplified equation, a is 1, b is 2, and c is 4. Let's substitute these values into the formula. We get negative 2 plus or minus the square root of 2, squared minus 4 times 1 times 4, all divided by 2 times 1. This simplifies to negative 2 plus or minus the square root of 4 minus 16, all divided by 2. This becomes -2 plus or minus the square root of -12 all over 2. Here's the critical point. We have the square root of a negative number. In the realm of real numbers, this has no solution. The solution involves imaginary numbers, specifically I. The square root of -12 can be written as I times the square root of 12, so we get -2 plus or minus 2i times the square root of 3 all over 2. Dividing all terms by 2, we find two possible solutions for a, -1 plus I times the square root of 3, and -1 minus I times the square root of 3. So, we have found two solutions for a, -1 plus I square root of 3, and -1 minus I square root of 3. But are these our final answers? This brings us back to the very first step of our problem, where we established a crucial condition. We determined that the value of a could not be 2, because that would lead to division by 0 in the original equation. We must check if either of our solutions violates this condition. Our first solution is a complex number, -1 plus I times the square root of 3, which is clearly not equal to 2. It is a valid solution. Our second solution is also a complex number, -1 minus I times the square root of 3. This is also not equal to 2. It is also a valid solution. So both of the solutions we found by solving the quadratic equation are valid solutions to the original problem. The solutions are a equals -1 plus I times the square root of 3 and a equals -1 minus I times the square root of 3. We have now solved the problem completely. Let's quickly recap our journey to the solution. We started with what looked like a complicated fraction. First, we identified and handled the constraint on the denominator by stating that a cannot equal 2. Then, we factored the numerator using the difference of squares formula, twice in a row, which is a common trick in these types of problems. This allowed us to simplify the equation by canceling the a2 terms, leading us to a quadratic equation. Finally, we used the quadratic formula to solve for a. And then we confirmed that our solutions did not violate the initial constraint. As you can see, this problem is not about a magical entrance exam. It's a testament to the power of careful step-by-step algebra. I hope this walkthrough was helpful.